Welcome to the lecture today. In our previous lecture, we have discussed about um, motion in and circular orbit around a gravity center. Now we would like to have a generalized discussion on elliptical orbits around a gravitational center. But before that, we want to briefly review how Newton discovered the law of universal gravitation. That is an interesting story, and I think it's quite instructive to let you know how Newton arrived at the law. It's not as simple as the usual story tells. Now, people usually when people ask you about how Newton discovered the law of gravity, they probably will refer to this picture or this story that an apple fell on the head of Newton, and suddenly Newton realized that there's a force of gravity attracting the apple downwards. Now, but that is not the. I don't know if that is a true story, but that of course is not the whole story. I would say that is not the whole story. Not because Newton actually discovered gravity, not because of the apple. Because I think a lot of people, including you or me, have seen objects falling down from a great heights. But we haven't. The people didn't think about that. That is related to the force of gravity, except Newton. Why? Because Newton. Let me complete the story. I make up another half. After Newton is being hit by the apple, he looked upon the sky, and he suddenly realized that there was a moon in the sky. And he suddenly realized that the moon was attracted to the Earth, actually by the same force of gravity. And he postulated that an apple falls to the Earth by the force of gravity, and the moon is also revolving around the Earth, also by the force of gravity. He has an insight. He has an insight to see that everything that is attracted to the Earth is bounded by the universal force of gravity. That is his unique insight. Now, not only that, not only the insight is enough, but he proceeded to prove that the force of gravity is inversely proportional to the square of the distance. That is the most important step. Now, how Newton did that? Now, I tell you now. Newton, at this time, he already knows that by the experiment of Galileo, he already knew that the acceleration due to gravity near the surface of the Earth is 9.8 meters per second squared. This is the number he knew. Okay, he knew. And he can also calculate the moon's centripetal acceleration. Well before Newton, at around, I think, 300 years before Christ, people had the Greeks, ancient Greeks has already measured the distance to the moon. Okay, they already know the distance to the moon, and they also know the period of the moon around the Earth. Okay, and so by these two pieces of information, Newton was able to calculate the acceleration due to gravity at the position of the moon. Okay, the acceleration due to gravity is simply the centripetal acceleration. If we assume the moon's orbit is circular, that's simply the centripetal acceleration, right? The centripetal acceleration is given by r omega squared, where r is the mean distance to the moon, and the omega is the angular velocity. If I convert the angular velocity into radian per second, I can omega can be written as 2 pi over the period of the moon, where the period of the moon in terms of second can be written at this figure. Now, 27.3 is the number of days. The moon revolves around the Earth once in 27.3 days. And this number are just converting the number of days into the number of seconds. So 2 pi divided by the period is the angular velocity. And I have the angular velocity square multiplied by the mean distance to the moon. I got the acceleration due to gravity. at the position of the moon. Okay. Now, but Newton then calculate the acceleration due to gravity at the position of the moon to the acceleration due to gravity on the Earth's surface. He calculated that ratio. Okay, and that ratio turns out to be this number, 2.78 times 10 to the power minus 4. Okay, so at the position of the moon, the gravity force is much weaker. The forces, the gravitational field strength is much weaker than that at the ground level. Okay, because the moon is substantially farther away from the center of the Earth. So that's why the gravitational field strength there is much weaker. Now, not only that, Newton actually knows the shell theorem. So the gravitational effect of the Earth, if you assume the Earth to be a spherical object, a spherical symmetric object, then it is equivalent to a point mass. The gravitational force is equivalent to the point mass as a center, right? So I can also calculate, Newton can also calculate the ratio of the radius of the Earth, that is capital R, to the distance from the center of the Earth to the moon, which is small r. So this is the Earth radius, and this is the moon distance from the center of the Earth. And he found that this ratio is 0.0166. Now, if I square this ratio, that is, I find capital R over small r square, I find that this is equal to 2.75 times 10 to the power minus 4. Now, these two numbers are very close to each other. They are very close to each other. The difference is about, I think, about less than 1%, around 1%. But there are other irregularity of the Earth, and there are all other complicated facts that the moon is not in circular orbit, etc. If you allow for that, these two numbers are actually equal, almost equal. Okay, and so you have the ratio of the gravity of acceleration be equal to the inverse, the square of the ratio of the distance. So that implies the gravity force or the gravitational field strength is inversely proportional to the square of the distance. Is that right? If these two ratios are equal, that means G is inversely proportional to R squared. So that's why Newton discovered the law of universal gravitation. That is the exact form. The gravity force is proportional not to the distance or to the inverse of the distance, but to the square of the inverse of the distance. Okay. Now, Newton can also work back from Kepler's third law. Kepler at that time has already found that the square of the orbital period of the planet is proportional to the cube of the orbital radius. He already found that. Now, if we can work backward, I just recall the previous slide. Now, this is how I derive the Kepler third law, right? Not this slide. Now, this is how I derive the Kepler third law, right? Now, but if I assume this, I don't know the constant. The constants are not important. I only assume t squared equal proportional to r cubed. Okay. I assume circular orbit for simplicity, and then I work back. If I work back, I will find that the velocity in a circular orbit is actually proportional to 1 over square root r. And if I work one step back, assuming this to be the centripetal force, then I can find that the gravity force is actually proportional to 1 over r squared. That is another way for Newton to see that the gravitational force is in fact proportional to the square of, inversely proportional to the square of the distance. Okay, so combining these two observations, Newton conclude by confident that the inverse square law of force is true. Okay, that is how Newton discovered that. He did not discover that by simply guessing. He discovered that but with evidence. he concluded from the experimental data that Kepler has arrived, and also the data about the moons revolving around the Earth. Okay. Now, how did Newton arrive at the fact that the gravitational force is proportional to the mass of the object? Now, Newton found that G, the acceleration due to gravity, is actually independent of mass. So it doesn't matter if you put the apple or the moon at this position. If you put the apple at the orbit of the moon and let it has a velocity that is equal to the moon, the apple will still go around Earth just like the moon. Okay, the acceleration due to gravity is in fact independent of the mass of the object. Okay, so if you put an apple here and let it have the same velocity at the moon, it will still goes around the Earth with the same period, just like the moon. Okay, so that means the G, that the acceleration due to gravity, which is by Newton's second law, it is the acceleration A. And so A equal to F over m by Newton's second law is independent of the mass of the object. Now, so if the force F divided by m is independent of the mass, that means the force must be proportional to the mass. Okay, otherwise I cannot have the G be independent of the mass, right? The only possibility that I can have the m cancel is that the F itself is proportional to m. If F itself is proportional to m, then when I divide it by m, I will have the m cancel, and I will get a G that is independent of mass, right? So that is the only possibility. But gravitational force is mutual. If the gravitational force depends on the mass of the apple, and also or the mass of the moon, it must also depend on the mass of the Earth, right? Because they attract each other with a mutual force. So it must be depend on the mass of both objects. So that means the force is proportional to the product of the mass of the two objects, and it's inversely proportional to the square of the distance. Okay, so that is a beautiful story in the history of science. That is how Newton arrived at the inverse square law force of gravity. Okay. Now we come to a slightly more difficult elliptical orbit, but I would like to say that it's not possible at this level. It's not possible for me to teach the elliptical orbit in full detail. The reason is that exact solution of the elliptical orbit requires solving a difficult differential equation. And I'm not going to teach you that differential equation at this level. This is an introductory course, so I would not prefer to teach you about that. So that is too difficult for you. So we will not go into the detail. We will just state some of the result, some of the important result. And I would like to first introduce Kepler's law of planetary motion for elliptical orbit. Now, Kepler's first law states that planets move around the sun in an elliptical orbit. First, we want to know what is an ellipse, how to draw an ellipse. Okay, that is the question. And ellipse actually has two foci. That is the plural form of focus. Now, how do we draw an ellipse? We use two pins. We pinned it on the cardboard, on a board, okay? And then we use a string, an inextensible string, to form a loop, okay? To form a closed loop. And we use the pencil to stretch the loop of string against the two pins, so that when the pencil goes around the two pins, it forms an ellipse. It draws an ellipse. Okay. Now, so what would be the mathematical relationship if I do that? Okay. Imagine now you have a loop of string with a fixed length. Now a pencil move around the string with the string fully stretched, move around, and the ellipse will come out. So what is the mathematical relation between that in that operation? Now, in drawing a circle, you know that the distance between the pencil, the locus, and the center of the circle is a constant, and that's a radius, right? The radius remains a constant when you draw a circle. Now for an ellipse, the distance from any points is not a constant, right? They keep on changing, but there is something that is constant, that remain constant. It's a sum of the distance between the pencil and these two foci remains a constant. Now, each of the distance is not a constant. You see when the pencil move, this distance and this distance, they keep on changing. But if I add them up, if I add these two distance up, then the distance remains a constant when my pencil goes around the pins in circle. Okay, that is the equation for an ellipse, and that is how we define an ellipse. The sum of the distance between the locus and two fixed point remains a constant. Okay. Now, why is it that? Because you see the length of the string is fixed. The string is inextensible. So the sum of these two distance must remain a constant, right? That is the idea. So this is the idea. The sum of the distance from the two foci it is a constant. Okay. Now let's draw a picture of an ellipse. The ellipse is like this. Now these are the two foci. Okay, these are for singular we have a focus. Okay. Now an ellipse has a long axis and a short axis. The long axis is called the major axis, and the short axis is called the minor axis. But people usually refer to not the major axis, but and the minor axis. They refer to half of it. So I denote A as a semi-major axis. So the distance here, the length of the major axis is now equal to 2A. So A is a half of the major axis, and B is half of the minor axis, which I call semi-minor axis. Okay, so the long axis is 2A, and the short axis is 2B. Now, if A and B are equal, that becomes a circle, right? But for the ellipse, A is larger than B. So the ellipse is slightly elongated, okay, on one side and slightly compressed on the other side, okay? Now, we define a quantity called eccentricity by this formula. Epsilon is by definition square root 1 minus B squared over A squared. Now, you can immediately see that because B is more than A, right? B is always more than A. And so this number is always more than 1. And 1 minus this number square root must always be smaller than 1, right? But it's always greater than 0 because B is not B is not 1. B is not equal to A, right? So the number is always greater or equal to 0. And it's also smaller or equal to 1. Okay. Now, if B is equal to A, then epsilon is 0, right? If B is equal to A, then this is 1. So 1 minus 1 is 0, and that becomes a circle. For a circle, the major axis and the minor axis are equal, and that is a circle, right? So epsilon equal to 0 means we have a circle. And if epsilon tends to 1, very close to 1, that means B is much smaller than A. Okay, so this is negligible compared with the 1. So epsilon is almost 1. And in that case, you get a very elongated ellipse. You imagine B is now very small. The minor axis is very short, but the major axis is very long. So you get a very elongated ellipse, almost like a straight line. Okay, and that is that's a very elliptical ellipse. Okay, so the so-called eccentricity actually means how elliptical, how elongated the ellipse is. If the epsilon is close to 0, that means the ellipse is almost a circle. If the epsilon is close to 1, that means the ellipse is very long, very elongated. Okay. Now let's have some important relationship between A, B, and epsilon. Okay, that's and also we will refer to this figure. Now we want to prove at the first we want to prove that the sum of the distance from the two foci is equal to 2a. We have to prove that. Now we draw an ellipse like this. Now these are the two focus. These are the two foci. Now this distance and this distance, they sum up to be constant. So I may call this distance R1 and I call this distance R2. Is okay? Now I consider a particular point. The particular point is here. It is along the major axis. Okay, suppose now I consider this point. So the R1, the distance R1 will become this distance, right? This is R1 now. And R2 will become this distance. Is that right? But the ellipse is symmetrical on both sides. So this R1 is equal to this R1. This is also equal to R1. Is that right? Because the ellipse is symmetrical. The two distance here must be the same. So that means if the length of the major axis of the ellipse is 2a, then R2 plus R1 must be equal to 2a. Is that right? So that means the sum of the distance between the two focus and the point of on the locus is equal to 2 times the semi-major axis. So that is an important result. You can see that remains a constant, and that constant is equal to 2a. Now we consider another point here. Sorry, I do not draw it very well, but I hope you can understand what I mean. Now I consider a point on the minor axis. Now this is the major axis. This x-axis is the major axis. This y-axis is the minor axis. So now I consider a point here. The distance from the point to the center is b, right? Because 2 times of the distance is the minor axis. So this distance is a semi-minor axis b. Now we consider two focus here. And the distance between this point and the two focus, the two distance add up to be 2a, right? We have proven that. So for this case, the figure is symmetrical about the y-axis. So this distance must be a, is that right? Because the sum is equal to 2a. Now the two lines are equal because it's symmetrical with respect to the y-axis. So the distance between this point on the y-axis with the focus must be equal to a. Okay. Now, so we have a simple relationship. By Pythagoras theorem, this distance must be equal to a squared minus b squared square root. Is that right? So this is the distance between the focus and the center of the ellipse. Okay. But as we know by definition, that's this distance, a squared minus b squared, is equal to a. I pick our constant a, and then this becomes b squared over a squared square root. Is that right? I just pick our constant a, and this becomes 1, and this term becomes b squared over a squared. Now this is by definition equal to what? Equal to epsilon, right? So this becomes a epsilon. So the distance between the focus and the center of the ellipse is actually equal to a multiplied by epsilon. Okay, so we arrive at this important result. Now I save this for you own study. And let me go back to this slide. I give it to you first in case I forgot. Yeah, so that's why we have this figure. Okay. Now at this point on the y-axis, we have A here, the two distance. The B is the minor axis, and the distance from the focus to the center of the ellipse is A epsilon, where epsilon is given by the eccentricity, right? It's the eccentricity. Okay. Okay, so we now know the basic of the ellipse. Now, Kepler's first law states that the planet moves around the sun in an elliptical orbit, with the sun located at one of the foci. Now, we'll have two foci for ellipse, and the sun is located at one of the foci. Okay, so the other focus is empty. I called it empty focus. And the closest distance from the sun is called the perihelion distance. The perihelion distance is the closest distance from the sun, which is here. Okay. This point is the closest distance from the sun, right, in the ellipse. And this point is the farthest distance from the sun, which I call the aphelion distance. Now, helion actually means of the sun. There's a word in Greek which means of the sun. So peri is the closest distance, and apt is the farthest distance from the sun. So the closest distance is R1 and the farthest distance R2. And the sum of the closest and the farthest distance divided by 2 is equal to the semi-major axis, because the sum of the distance is equal to 2a, right? So that means a is equal to the sum of the perihelion and aphelion distance divided by 2. Okay. So that is Kepler's first law. Now let's see about Kepler's second law. Now Kepler did discover this law not by calculation, not by theory. He discovered this law simply by looking, by manipulating the observation data of Tycho-Browne. Okay, by analyzing the observation data of Tycho-Browne, he arrived at this law. So this law are purely empirical. Kepler did not have any theory behind that. He simply looked at the observation data and he looked for a model that best fits this data. Okay, so eventually he discovered the planet does not move in circular orbit, but in elliptical orbit. Okay. Now here is the Kepler's second law. It says that when the planet moves around the sun, the speed of the motion will change with time. And there's a simple law relating the speed of an object at different position. Now suppose the planet now move from this point A to A prime in a certain period of time. I don't know what that period is, but let's say that is 1 month. So in a month of time, the planet moved from A to A prime. And now you can imagine there's a line joining the sun and the planets. So imagine a line joining the sun and the planet. So when the planet moves, the line swept out an area, right? And I call this area A, capital A. So when the planet moves from A to A prime, the imaginary line, or the so-called radial vector between the sun and the planet is just like it swept out a certain area, which I call A. Now, in the same, when the planet is in at another position B, in the same period of time, say 1 month, okay, the same period of time as in A, in the same period of time, 1 month, the planet now moves from B to P prime, and the radial vector swept out an area which I call B. And Kepler's second law says that the area vector joining the planet and the sun swept through equal areas in equal time. So the time for the planet to go from A to A prime and B to B prime are both equal to 1 month. the period of time are the same. So the area swept out by the radial vector in these two periods of time are also the same. So the area capital A is equal to the area capital B. Now you can immediately see from this law that when the planet is moving closer to the sun, it's actually moving faster, right? Now because the radial vector is short, okay, the distance between the sun and the planet is short. So in order to maintain the same area, you have to move faster, right? You have to have a wider area. So the planet actually moves faster when closer to the sun. When you are farther from the sun, the radial vector has a longer length, right? So that means the planet will move slower in order to get a very narrow but very long triangle area that matched the original area at A. Okay, so that's why the planet is moving slower when it's far away from the sun. So that is a law that tells you how fast the planet moves when it's at a different position from the sun. Okay. Now I will show you that this is not difficult, so I can show you. Kepler's second law is actually not a new law of nature. It can be derived from Newton's law of motion and Newton's law of universal gravitation. And in particular, the Kepler's second law can be derived from the law of conservation of angular momentum. If I assume angular momentum to be conserved, not assume, but I will show you that angular momentum is conserved in this case. And based on the conservation of angular momentum, I can arrive at at Kepler's second law of planetary motion. Now, why angular momentum is conserved? Consider the vector that points from the sun to the planets. So the sun has a mass capital M, and the planets have a mass small m. Now I have vector R pointing from the sun to the planets. Now the gravitational force is pointing towards the sun. Okay, so the gravitational force points in the reverse direction of the position vector. So F and R, they are in opposite directions. Okay. Now I know from the law of Newton's second law of rotation that the torque produced by a force is equal to the rate of change of angular momentum. So torque is equal to dl dt. That is what we learned in last chapter, right? We learned the law, Newton's law of in the rotational form. Okay. But what is the torque? I already introduced to you in the extension part of this chapter that the torque is given by R cross F, right? And what is R cross F here? Now, the torque is actually the product of the radial distance and the force multiplied by sine the angle between the two vectors. That is the magnitude of the torque. Okay. But now the two vectors are opposite to each other. R vector and F vector, they are exactly opposite. So the angle between them is 180 degrees, and sine 180 degrees is of course 0. So the cross product between two vectors that are in opposite direction is 0. So they are 0. Okay. So the torque becomes 0, and the LDT by Newton's second law of rotation is 0. And that means if the time derivative of L is 0, that means L remains a constant. L is a conserved quantity. So the angular momentum is conserved. Now you can see this proof actually hinge on the fact that the force is being opposite, in opposite direction to the radial vector. And so the proof applies for all so-called central force field. As long as the force is along the radial vector or in opposite direction to the radial vector, the angular momentum is always conserved. It does not depend on whether the force is inverse square law force or not. The important thing is that the force acts along the line joining the two objects. So for all the central force field, angular momentum is conserved. Okay. Now let's prove Kepler's second law for planetary motion from the conservation of angular momentum. Now, suppose at a certain instant, the planet is here. So the position vector of the planet is r. Now, at this moment, the planet moves a little bit. In a small time interval delta t, the planet move forward by a distance v delta t. So this period of time is small. So the distance moved by the planet is almost a straight line, denoted by this vector. Okay. And in this interval, the radial vector r swept out an area, and the area is the area of a triangle formed by the vector r and the vector v delta t. Okay. So this forms a triangle, and now we want to find the yellow area because there's an area swept through by the radial vector. Okay. Now we denote the angle between the radial vector r and the velocity of the object by the angle theta. This is the direction of motion, okay, characterized by the velocity v. So v delta t becomes the distance traveled by the object, okay, and the radial direction here is outwards. So the angle between them is, I call it theta. Now I want to find the area of the triangle, the yellow area. Now I just apply the equation for the area of a triangle. That is 1/2 the base of the triangle. The base of the triangle is of course r, multiplied by the height of the triangle. Now, but the height of the triangle is here, right? It's this line, this dashed line. It is equal to v delta t sine theta, right? Because this is the line perpendicular to r, so there's not simply v delta t, but v delta t multiplied by sine theta according to this right angle triangle, right? So we have 1/2 the base multiplied by the height, which is v delta t sine theta. That is the height of the triangle. Okay. We divide the equation by delta t, so we get rid of the delta t on the right-hand side. And in the limit delta t tends to 0, the delta A over delta t becomes the ADT. The area, the rate of area swept through by the radial vector. And the rate of area swept through by the radial vector is now equal to 1/2 RV sine theta. Now we are going to prove that this quantity is actually proportional to the angular momentum of the planets. How do I prove it? Well, I know that the angular momentum is r cross p, right? That is my definition. And in terms of the mass m and v, that becomes mr cos v. And so the angular momentum divided by m is just the magnitude of r cos v. And it's rv sine theta, right? It's rv sine theta. Because the angle between the two vector is theta. So the magnitude of r cross v is rv sine theta. Is that right? So the angular momentum divided by the mass is rv sine theta, which is exactly this guy, apart from the factor of 1/2. So now we have the ADT be equal to L over 2m, but that is a constant. M is a constant, and since angular momentum is conserved, L is also a constant. So the ADT is a constant, which means that the area vector, the radial vector now swept out an area at a constant rate. Okay, this is just the Kepler-second law of planetary motion. Okay. Now we can also have the third law. Now for the third law, I will not proceed with the proof. It's quite tedious. I'm not trying to confuse you here. I just state the result. Now for Kepler third law with circular orbit, I know that t squared is equal to 4 pi squared gm multiplied by the cube of the orbital radius, right? That is Kepler third law for circular orbit. Now how about elliptical orbit? If the planet moves around the sun not in perfect circle, but in ellipse, how would we modify Kepler third law? The answer is quite interesting. It happens that we can just write down Kepler's third law in the same form, just by replacing the orbital radius with the semi-major axis of the elliptic orbit. So now we don't write R, but we write A, the semi-major axis of the elliptical orbit. Okay, so now T squared is equal to 4 pi squared over GM, the cube of the semi-major axis. Now I'm not going to show you the proof. In fact, that is not difficult, but just a tedious mathematics. I don't know. I don't want to confuse you now, but I just want to state the result that result is quite useful. And there's interesting features here. You can see the period now depends only on the major axis, but not on the minor axis. Okay, so that means interesting features. That means if you now have the sun here, and you have a planet moving around it in a circular orbit, or you have another planet moving around it in an elliptical orbit, as long as the major axis of the elliptic orbit is equal to the radius of the circular orbit, if R is equal to 2a, then the two planets will have the same period. T1 is equal to T2. It doesn't matter what the minor axis is. So even if you have a very long, very short minor axis like this, as long as this distance is still equal to 2a, okay, the period are all equal. Okay, now this is a rather interesting fact. I cannot have a proof for you. The proof can only be done mathematically. But there's an interesting fact that it does not depend on what the minor axis is. So no matter if you have a circular orbit or an elliptic orbit or whatever minor axis, as long as the major axis is equal to 2a, you always have the same period. Okay. Now, how about the total energy? How about the total mechanical energy? I also will not show you the proof. It happens that the total mechanical energy of a planet in an elliptical orbit is equal to this quantity. Now, we have proven that for circular orbit, the total mechanical energy, including the kinetic energy and the potential energy, they are equal to minus GMM over 2R, right? R is the orbital radius. We have proven that. Now, I let you see the previous slide in case you forgot. Well, we have this slide for circular orbit, right? The sum of the kinetic energy and the potential energy, we have proven that is equal to minus GMM over 2R, right? Where R is the radius of the circular orbit. Is that right? Now, this you are learning in high school, okay, also. I think when you learn about gravity, you learn the circular orbit around a gravity center, and you learn about the energy, right? Now, we extend it to a elliptical orbit. We just replace, it turns out that we just have to replace, again, the radius of a circle by the semi-major axis of the ellipse. We just replace R with A, and everything will work for elliptical orbit. Now, this is again unexpected, but the fact is like this. Okay. Now, but be careful. There's a major difference between a circular orbit and the elliptic orbit. is that for a circular orbit, the distance from the sun is keep on changing. Okay. For a circular orbit, this distance r from the sun, this is a sun, this is an empty focus. The r is keep on changing. So the potential energy U, which is given by Gmm over R, is changing all the time. And when the potential energy changes, the kinetic energy, which is given by half mv squared, is also changing. Okay, so both U and K, they are changing all the time. Okay, they are not constant. But it happens that if I form a sum of K and K plus U, which is a total mechanical energy. So the total mechanical energy is given by this. And that remains a constant. And that constant is equal to GMM over 2A, where A is the semi-major axis of the ellipse. Now, I would not show you the detailed proof, but in some of the exercise or some of the homework problem, you have to use this relationship. Okay, you have to assume the sum of these two terms be equal to a constant, and the constant is given by this. And so V and R are actually related. Okay, you can derive V for different R. If you put this term to the right-hand side and you take the square root, you can find V as a function of R at different position on the elliptical orbit. Okay, so that is a application of this formula. Now let's just have a very simple example applying what we have learned. Suppose for simplicity, we assume the Earth orbits and the Mars orbit around the sun are circular. Okay, so the Earth moves around the sun and the Mars moves around the sun in perfect circular orbit. That is a simplified assumption, of course. Now we want to send a artificial spacecraft from the Earth to the Mars. So what are we going to do that? How do we going to do that? Now, the easiest way to do that is to use a so-called Hoffman transfer orbit. Now, Hoffman transfer orbit is actually a elliptical orbit. The closest distance from of this elliptical orbit from is the distance, the Earth-Sun distance. So we take this to be the closest distance of the orbit from the Sun. And the fastest distance from the Sun is the Mars-Sun distance. Okay, so you can see this axis is actually the major axis of the ellipse. Okay, that connect the Earth and the Mars. Okay, you have this elliptical orbit around the Sun that connect the Earth and the Mars, with the Earth at the perihelion distance and the Sun, the Mars at the aphelion distance. Okay. So I assume that the Earth-Sun distance is 1 AU. AU is astronomical unit. The Mars-Sun distance is 1.5 AU. Okay. So what is the period of this dashed line? If the spacecraft are now projected in a certain way, such that it moves under the sun's gravity along this elliptical orbit, which I call Hoffman transfer orbit, I want to find the period of this orbit, and I want to find the time for the spacecraft to go from the Earth to Mars. Now we apply, because it's a motion around sun's gravity, right? So we apply Kepler-Third law in this form. Okay, T equal to A raised to the power of 3/2. We do not have to include a constant 4 pi squared over GM, because we now are studying motion around the sun as a gravity center, and we use the Earth year as a unit of time, and we use astronomical unit as a unit for length. So we have to, so we can skip all those constants. Okay, all those constants sum up to be 1. Okay. So T is equal to A to the raised to the power 3/2. But what is A? What is the semi-major axis of the elliptic orbit? It is a sum of the closest distance and the farthest distance divided by 2, right? So A1 plus A2, the Earth sun distance and the Earth mass distance divided by 2. Okay, and the transfer time is half of this. Okay, so we substitute this number into the equation. We get this combination, and we eventually find that it takes about 0.7 year to go from the Earth to Mars. Okay, so that is a transfer time. The minimum transfer time, well, not the minimum, but a typical transfer time for you to go from Earth to Mars is about 0.7 Earth year. Okay. Now we take a break first. We